Welcome back, everyone. In our last session, we got our hands dirty with gradient descent, finding that perfect best fit line for our linear regression model. But here's the thing. What happens when that perfect model runs into the real messy world? Well, today, we're going to put it to the test.
So let's start with the big question. We built this simple, elegant model. It's fantastic. But how do we know if we can actually trust it? Is it a solid foundation for making real predictions? Or is it, a delicate house of cards just waiting for a puff of imperfect data to come along and knock it all down? To answer that, let's just take a quick step back and remember why we like linear regression so much in the first place. It really comes down to its beautiful, beautiful simplicity.
I mean, the promise is just so tempting, right? You get a single straight line that best explains the trend in your data. And the math, the ordinary least squares we talked about, guarantees that we can find this one unique solution. But, and this is a big but, that guarantee comes with some serious fine print. A hidden set of rules that our data has to follow.
Think about it like this. Any good model, just like a building, is based on a very strict architectural blueprint. And if you want that building to stay standing, you have to follow the blueprint to the letter. Well, for linear regression, that blueprint is what we call its assumptions. And here they are, the 5 foundational rules. First, the relationship you're modeling has to actually be a line. Kind of obvious, but you'd be surprised. Second, your inputs can't be telling you the same thing. And finally, the errors, those little mistakes your model makes, they have to be well behaved. They need to be consistent, totally independent of each other, and they should form a nice classic bell curve. So, let's see what happens when we start breaking these rules. So, what happens when our data doesn't feel like following the blueprint? Well, that's when cracks start to appear in our foundation. And when the foundation is cracked, our predictions, they become basically useless. So how do we spot these cracks? We look at the errors, or what we call residuals. A healthy model has residuals that just look like a random cloud of dots, no pattern at all. But if you see something like this U shape, that is a huge red flag. It's screaming at you that you're trying to force a straight line onto a relationship that is clearly a curve. Your model isn't capturing the real story. We call that underfitting. Okay, rule number 2 is all about redundancy. This one's a classic. Imagine you're trying to predict someone's salary and you use both their age times their years of work experience as inputs. Well, those two things are super correlated, right? They basically tell you the same story. This just confuses the model. It has no idea how to assign importance to age versus experience, so the weights it comes up with become totally unstable and basically uninterpretable. All right, next up is homoscedasticity. And listen, don't let that fancy word scare you. It's a really simple idea. The size of your model's mistakes should be consistent across the board. If your error plot looks like that random cloud again, you are golden. But if you see this funnel shape, that's a huge problem. It means your model's accuracy changes. Maybe it's great at predicting low house prices, but absolutely terrible at predicting expensive ones. When you see this, any confidence intervals you calculate are just plain wrong. And the last 2 cracks are really about the statistical trust we can put in our results. First, if your errors aren't independent, this happens all the time in stock market data, where yesterday's error influences today's, then all your statistical tests, like p-values, are basically meaningless. And second, if those errors don't form a nice bell curve, especially if you have a small data set, then the confidence intervals you put around your predictions, well, you just can't trust them. So those are the cracks in the foundation, the violated assumptions. But that's not all. There are 2 other major limitations that are baked right into the math of linear regression. I like to think of them as wrecking balls, just waiting to smash our model to pieces. Remember our cost function, the sum of squared errors, the one we worked so hard to minimize with gradient descent? Well, that is our first wrecking ball. We square the errors because it gives us that perfect convex bowl shape with one single minimum. It makes the math work, but that mathematical convenience, it has a really dangerous side effect. Here it is. Because we are squaring the errors, just one single outlier gets a massively oversized boat on where the line goes. Look at this. On the left, a nice, clean data set. On the right, we add one outlier. That point's error is so huge that when you square it, it literally yanks the entire line towards it. Your model isn't modeling the data anymore. It's modeling that one crazy point. And that brings us to the second wrecking ball. This one is even more fundamental. Let me just ask you a simple question. Can a house have a price of negative $20,000? Of course not. That's ridiculous. But
What does our model think about that? Linear regression's answer is sure, why not? Because a line goes on forever in both directions, our model has zero concept of a ground level or a real world boundary. So if the data trends that way, it will happily predict impossible values. And this points to a fundamental mismatch. We're using a tool made for unbounded numbers to predict something that, in reality, can't go below zero. So, after all that, where does this leave us? Well, understanding the blueprint isn't just about finding problems. It's about knowing when to put the blueprint for linear regression back on the shelf and pick a totally different design for a totally different problem. So this is the big takeaway. This is your pre-flight checklist. From now on, before you even think about using linear regression, you have to run through these questions. Is the relationship actually a line? Are my features redundant? Are my errors well behaved? Are there crazy outliers? And can my prediction be negative? If you get a no on any of these, that's a huge warning sign that you might be picking the wrong tool for the job. And that leads us to the final, most important question of all. If this simple blueprint doesn't fit our problem, what do we build instead? Answering that question is what separates the good data scientists from the great ones. And it is exactly where we are headed next on our journey. Thanks so much for joining me, and I'll see you in the next one.